also offer digital we also offer digital resources and coordinate a range of events, including summer schools, conferences, workshops, webinars, and meetups. We provide grants to support the establishment of research programs, and we're also actively engaged in policy conferences to foster policy-related discussions and thoughts around AI and climate change. Additionally, we bring together a vibrant community that stays informed through our newsletter and through our community platform. For more details, you can visit our website, which is linked over here, climatechange.ai. All right. By joining our community platform, you'll gain access to information about climate change AI and also have the opportunity to connect with people interested in various areas of application. We also have a blog that's updated with technical blog posts on various application areas in this domain. These are available to everyone, and they cover a wide range of topics, including research applications, and then also presentations from our team. If you're interested in what we do, you can follow us on Twitter and also subscribe to our newsletter, where you'll have various updates about conferences, funding opportunities, recent projects and articles, and also job opportunities. To make this webinar interactive, please connect to the associated Slido link, which I think has been posted in the chat already. You'll be able to ask your questions on this platform and also upvote other people's questions. And eventually, the questions with the higher number of upvotes will be more likely to be asked. So make sure you get your thoughts in there. Now, without further ado, I'd like to introduce our speakers for today. So we've got Tobias and Marcus, who've graciously given us their time to talk about this tutorial that they've developed. So Tobias Brudermüller is a PhD candidate and doctoral researcher at the Bits to Energy lab at ETH Zurich. In his current research, he develops machine learning techniques for energy applications to promote sustainability and further digitalization of the power grid, with a focus on optimizing residential heat pumps. Tobias has a background in electrical engineering and computer engineering. He holds a master's degree from RWTH Aachen in Germany and 2 bachelor's degrees from the Technical University of Darmstadt. Additionally, he was a visiting researcher at Yale, founded a startup in the area of augmented reality, and has also worked for and with multiple companies, including Google, Bosch, Mercedes, SAP, and Merck, SAP, and Merck. Our second speaker, Marcus, is also a PhD candidate and doctoral researcher at the Bits to Energy lab at ETH Zurich. Siri is interrupting me. Sorry, Marcus. So Marcus is a PhD candidate and doctoral researcher at the Bits to Energy lab at ETH Zurich. His work focuses on incentive structures that enable a high share of renewable energy sources in the power grid. He uses tools based on optimization and learning algorithms. And he holds a bachelor's and master's degree in physics from Heidelberg University. There, his research focused on the dynamics of biologically plausible neural networks. He specialized his studies on statistics and data analysis, as well as machine learning. Marcus has industry experience in project management from working in the infrastructure sector. So without further ado, let's have the 2 speakers take it away. And thanks a lot for being here today.
Great. Thank you very much. Then I hope you can see our slides full screen. Perfect. Yeah, so thanks for the introduction. So we are both colleagues at the Bits to Energy Lab, as it was mentioned, at ETH Zurich, and also dialing in from Switzerland. And yeah, we are here with a practical tutorial, walking you through a practical tutorial that we've made for ICLR workshop hosted by Climate Change last year. and it was also part of Climate Change AI summer school last year. And so we will walk you through that. But that being said, we really hope to get your questions as well, and to get into discussions. So maybe not the whole time we will just be talking. Maybe there will be some questions on your end, depending on how the process is. So the Bits to Energy Lab is just a few words about that. Is actually a team of approximately 20 researchers with different professional backgrounds, so really from psychology to electrical engineering. And we are located in Germany and Switzerland. And the idea of this is that we leverage technology to foster sustainability, where we put a special focus on machine learning, energy applications, and digital behavioral interventions. So yeah, for example, there was quite a lot of work from our lab also on smart meters for showering that really give you like real-time feedback on how much energy you use during showering. And with that, it was shown that the energy consumption is actually reduced by approximately 15% by just providing feedback to the users while they are showering. And so this is the kind of research that we do here at the chair. And of course, otherwise you wouldn't be here and be interested in these topics. You probably know about the Sustainable Development Goals from the United Nations, and the ones that we are working into or working for are affordable and clean energy and climate action. In that sense, also the reality actually is that some countries suffer from energy poverty and just do not have access to enough energy, while other countries have a lot of access to energy, which depends also on the degree of industrialization. And this is the second problem, that these countries that have a lot of energy available actually have too high carbon emissions. And this is what we are trying to tackle here. Concerning the energy system, we actually see on the generation side quite a big shift. We see that the wind electricity generation increases quite a lot. So these are numbers here from the International Energy Agency. And the share of wind electricity generation has changed within just 1 year by 55%. And the same holds for solar and PV generation, which increased by 22%. On the other hand, what the electricity system faces is still quite an old infrastructure when it comes to distribution. So, for example, this is a report showing that 70% of the power transformers and transmission lines in the US are at least 25 years old. On the other hand, we also see quite a big increase in global annual grid scale battery storage additions, which is good news, but it's still not fast enough, actually. And last but not least, on the consumption side, we see a very high increase of electric vehicles being added and heat pumps being added to the grid, which means an increase in electricity demand. And that being said, not only the electrification in all sectors and the private sector lead to an increased electricity demand, but also population growth and an increasing access to electricity, which is, of course, what we want. On the other hand, that brings some problems to the electricity grids, not only this higher electricity demand, but also the large fluctuations in electricity productions, which come from this increasing share of renewables and this high degree of decentralization that I just mentioned before. And all of that together means that we need new solutions to tackle these problems, and that means smart control, energy storage, more energy efficiency, these sort of things. And that is where the advanced metering infrastructure comes into play. And of that, when I'm talking about that, I mean in particular smart electricity meters. So you can imagine these to be devices, same as electricity meters that you might know from your home, these analog ones which have turning wheels going up the more electricity consumed. These are basically just a digital version of that transmits electricity consumption in a regular interval to the utility companies. And here we can see quite high penetration rates in industrialized countries. So in the US, in 2016, already approximately 50% of the buildings had a smart electricity meter installed. And in China, India, Japan, and South Korea, reports say that it's 69% already in 2019. And the EU, in the EU, it depends very much on which country you're looking at. There are some countries that are basically at 100% rollout rates and are currently deploying the second generation devices, while other countries are a bit left behind. But overall, the goal of the European Union is to achieve 80% rollout by 2025. Maybe keep with these numbers in mind that it's quite difficult to prove on how high these numbers are in the end, really. But yeah, we can see still quite high penetration rates, and it will increase. And that enables the so-called smart grid, which basically means all sort of digital activities on the grid, from monitoring to decentralized control to enabling demand response programs, to providing incentives by dynamic tariffs, to planning and forecasting. So really all sorts of applications. And of course, it also enables new digital services that can, for example, be providing feedback about energy efficiency of buildings, but also smart buildings in general and retrofit, so smart homes, controlling electric vehicles for charging operations, and also optimizing heat pump operation, as these two are just quite high consumers in the residential sector. When we talk about smart meter data, as we will now in a bit when we walk through the tutorial, that means that we're talking about time series data of power or energy measurements at different resolutions. So these can be from 1 second to 1 hour, for example, or even daily resolution. We will later mostly talk about energy data and not power measurements, but Markus will dig deeper into that in a bit. And what this looks like, for example, is shown here in a graph. That is electricity consumption in form of electrical energy in 15-minute resolution. And you can really see these very nice patterns over just a few days. So this is just a plot over 1 week. And here on the left, you can see what a smart meter looks like as an example. The goal of this tutorial that is provided online and that you can also walk through by yourself for self-paced learning is to provide you insights into the energy domain in general, so give you some hints on current trends and use cases in the energy space, but also to provide you a feeling, for you to get a feeling on what is typical and atypical energy use in residential buildings and what is the value of smart meter data and smart grids in general. At the same time, we also want to support climate change AI in educating about data analysis in general. And that being said, this notebook that we provide there, or this tutorial, is really like very practical, hands-on. You can do it in a self-paced learning manner and really practice your skills, try to adjust the code, and yeah, and this way learn how to apply best practices, how to apply machine learning, and maybe ultimately in your use case deliver it also within a real world setting. So we really use also real world energy data in this tutorial. And yeah, maybe it's a starting point for you to also start analyzing energy data. And yeah, last but not least, with that, we also want to create awareness for energy efficiency, your own energy use if you have a smart meter available. Maybe here a hint, at least in the European Union, you are eligible to download your smart meter data if you have a smart meter installed. So basically under the data privacy regulations, the utility company must provide you with the data if you request it. So you could really send an email to your utility company and ask if you have a smart meter, and if yes, how you can get access. Sometimes there are online portals for it. Sometimes they will just provide you with CSV files. But so in case you have access to a smart meter, maybe go and use it, use this tutorial and apply these techniques to your own data. And yeah, I will not give a very detailed overview now on what this tutorial is about, because we will walk you through it in a bit, but maybe just the headline so you at least know what you will look at. So we will give a short introduction into what smart meter data is. Then we will give some best practices for visualizing this type of data and for pre-processing it for further use. And next, we will show you some really like practical applications, which are, for example, non-intrusive load monitoring. So meaning disaggregating single appliances from a measurement of only total all appliances together, basically. Some anomaly detection, some flexibility estimation, and also some load forecasting. Customer segmentation, meaning, yeah, grouping types of similar customers. And last but not least, we will also provide you with some additional resources, some data sets and software packages that you can check out. And with that, I think I would hand over to Markus, and we will basically just walk you through the tutorial.
Exactly, yeah. Thank you very much, Tobias. So this is the tutorial. It's just a Google Colab, but you can also download it as a Jupyter notebook for yourself. It's hosted on GitHub. And yeah, we provide a brief introduction and have a nice outline where you can see all these steps that we just listed on the slides as well. And now we'll just walk through it, starting with the background on smart meter data. And you've already learned from Tobias now in general what it is. We're working with time series data. There are different kinds of resolutions. One point that Tobias mentioned is the question of power versus energy. And I want to show just a little bit deeper there. You might be familiar from physics classes or engineering that with alternate current, if you have power, you have basically different components of your power. So this would be active power and reactive power. And then you can also have a phase angle between those, for example. So this is quite detailed information on the energy system. And some smart meters are indeed able to measure such data. However, commonly it's also just that there's basically an energy value of the total energy consumption in a certain time window given. And this data is just transmitted to the utility, ultimately also for billing purposes, for example, because that's in the end what you pay for, what the utility needs to know about you. And so this is why in our tutorial here, we basically make use only of this 15-minute interval energy data, because this is most commonly available. So yeah, this also covers sort of the data resolution Tobias mentioned from second level, basically, up to hourly data, sometimes even daily data is what's commonly available. However, again, here, what the utility in the end gets is, in Europe, there's sort of a standard for around 15-minute or 30-minute data. It depends a little bit where you are. But this is just round about what you can get. So this is what we are also using. Then if you have like data sets, I mean, you might be familiar in general with problems with working with data. Tobias mentioned there is an increasing rollout of smart meters, but this also means not all the smart meters are available at the same time. And you have common problems of just, when is the data available? Is there missing data? What happens in case of an error in transmission of the data? So these are points that you have to keep in mind when working with smart meter data, potentially also with your own smart meter data. Then one additional sort of data source that can be very insightful is any kind of context information that you have. So instead of just having a time series of data, it might also be interesting to know where does this data come from, in the sense of what kind of building is it? Is it single family house? Is it like a multifamily residence? What size is the building? Is it well insulated? How many people live there? All these questions, they can help you understand better the data, and you can also use it for the later methods as an additional information. And yeah, sort of related to that, not only the context data, but also additional data. And this is also something we will be using here. For example, very insightful can be temperature information and other weather information, because this can, again, explain a little bit better what's going on, and you can understand the data better. And this would, of course, be also time series data, for example, of temperature or the irradiance of solar power. Can be very interesting. So with this sort of background on smart meter data and other kind of data, we jump right into the code of the tutorial sort of, and this is really where the practicality of it comes in. That it's really we include here all the packages that you need. So it's of course written in Python, making use of most of the common machine learning and data science packages. And then we provide some functionality to just download some smart meter data from just a few households. And this is what we'll be working with then. And this is of course also what you can make use of. And so this brings us to the sort of the first time that we see now this smart meter data. It's here just in a pandas data frame, so just in a table basically. And we always have the timestamp of the consumption and then a value. And in our case, this is, like I said, it's energy measurements for the given timestamp and then the following interval. And you can see here it's just 15-minute resolution data. And what you can also see here, it's not only one power value, but actually we have three, because we have separate values for a heat pump that's installed here at this household, and for all the other appliances together. So all the lights, the stove, or the outlets, everything else. And we will see a bit later again why especially this heat pump might be interesting to know more about. And then also we provide some functions to get some weather data, as I mentioned, as additional context. And now, of course, looking at this data in a table is a little bit difficult and not so insightful. So the first step really for me always, and commonly in data science, is you try to look at the data. You try to look at it from different angles and understand what's going on. And that's why we present some different functions to plot this data. And there we for example, have here this overview. Of course, we can just take this time series and just plot it all. And then we see it spans from 2020 to 2022. And we can already see a few patterns over the year, but it's just a lot of data. Every 15-minute a data point. This really is a lot. So what you can, for example, do is you can sum up the daily consumption, and then you get a little bit of a better idea, and you can see the seasonality in the data between the summer seasons and winter seasons already much better. As an alternative, you can also, for example, zoom into the data, just taking a look at a single week. So this is also what Tobias showed before, the kind of regularity you can see on a weekly level. Or then another very interesting way is to not look at sort of single day data, but to sort of sum it up all and look at the profile of data over the day. And here already you can see very interesting patterns, because you basically have at every hour the average demand over the whole time period, how much power was drawn in this hour. And we can, for example, see this very interesting peak here at around midnight in the late evening. And we'll later talk a bit more about what this could be, for example. Then also other angles, as I mentioned, for looking at data. You can also not look at it in the time domain, but sort of build a histogram of consumption values. So here you count how often do I see which level of power consumption. And then you get a graph, something like this, where you can basically see that there are some power consumption values that occur a bit more often than other ones. You can also see this especially in a logarithmic scale. Then you have some peaks here, and this of course can mean that maybe there's something interesting going on with this, with power at this draw. Like maybe there's a device that draws exactly this much power. And then finally for visualizations, also a very nice way to look at it is actually in a two-dimensional manner. So here we split up the time axis into the date and the hour of the day. And then basically for every day, we have here one of these columns in the plot. And here we see some really interesting patterns that go beyond what we were able to see before. So we still have over the date, we have the seasonality between winter and summer months, but also over the day along the y-axis, we also see some additional patterns. And for example, again, we see this interesting thing happening here at night around midnight that we'll, like I said, talk more about a bit later. So then also other options are to look at like three-dimensional plots. And here we see, for example, spikes really well. They are really nicely come out in this kind of plot. And then this is there's a figure I really like where you basically combine everything. You have the daily consumption values, the daily power peaks up here. Then you have the mean demand profile on the side, and you have this nice heat map showing the two-dimensional data. And this can just be very insightful to understand and also compare data. For example, what I've also annotated here is put in these white lines. These are just the sunrise and sunset times. They jump here. This is due to daylight saving time. This is always a bit of an issue when working with time series data. But basically, if you, for example, talk about solar generation, this can be very insightful to see when is the sun shining and when is it day, when is it night? How does that influence power consumption? Yeah, and then finally, as I mentioned, in the specific data that we have here now, we have actually not only the total demand, but we have demand from the general household and then from the heat pump, and we can also sort of plot this together and then plot them on top of each other, and then we can, for example, see periods where there's a lot of heat pump demand, but no other demand, and so on. So this can be also an interesting way to look at multiple data streams simultaneously. And now I'll hand over to Tobias, and he'll talk a little bit more about what to do with this raw data and how to continue from there.
Yes, thank you. Maybe that being said, once more going back to this plot. So what we really learned over time is that we have looked at these plots for thousands of households. And we really learned to get a feeling for, okay, why is this pattern happening? What kind of household is it? Does it have a heat pump? Do they have an EV? Do they have a PV system, so photovoltaic system? Because then here you would see like big holes in the middle, because basically no energy will be drawn from the grid, but the PV system provides everything the household needs, and then you really don't see anything here on the smart meter. So what we would really recommend is, if you have access to a lot of smart meter data, to get to learn these sort of heat maps quite well, because it will really help you. And generally be inspired by what is it that you are trying to achieve with the data, and how can I actually display it and visualize it. And that is not like aggregating it across all households, but really looking at individual households and making some sort of these differences between individual households visible in the data, because that will give you a good feeling for it. I know it's complicated, but that is the only thing I wanted to add here to this visualization part. Then, as Markus mentioned, you can have like a lot of problems within the data. You can have gaps, you can have, I don't know, peaks, erroneous measurements, and that informs how you want to pre-process the data for further use for as input to any other method. And the first thing we do here is, you saw previously that we had data frames including the weather data, and data frames including the smart meter data. That is actually quite complicated to handle. You can imagine that it's more intuitive if you have everything in one table, which is what we do with this method here. So basically, we just use the timestamp to merge these two data frames together with the weather data and the smart meter data, and then you have them next to each other column by column. And that enables quite a lot of things on looking at the temperature dependency of the electricity data. So for example, here you can just very easily calculate the correlation of the average day temperature and the energy drawn. And you can see here that it's quite well correlated in a negatively correlated. And what you then often do is, because people don't like negative correlations, but positive correlations, is that they calculate the so-called heating degree day, which is basically a measure for how big is the heating part that you need to fill. So this is actually quite easy formula, which is standardized. So you assume some sort of mean outdoor temperature of the day is the actually measured temperature of that day, and then you assume some sort of room temperature that you would want to heat to, and then you have a Boolean value if the mean outdoor temperature of the day is below the heating limit or not. So that means that the heating degree will give you a value of 0 if there is no heating active. And beyond that, if there is heating active because it's cold outside, then you will get a value. The higher it is, the more heating is required. And if you do that and then calculate the correlation across this heating degree day value, then you will get a positive correlation. Or you can use it for filtering. So if you use it to filter just on finding heating days. And similarly, there is the same for cooling degree days where, there are also standardized measures out there. Actually, if you just Google heating degree day, you will find sorts of standards and definitions across countries. So in Germany, there are different standards than in the US, for example. Here is a method that you could adapt for your use case and then calculate that. And if you then plot the energy consumption, for example, as box plots, so as individual distributions per heating degree day, you will see exactly this positive trend. The bigger the heating degree, so the bigger the delta to be heated, the more electricity will be drawn. And of course, we chose a good example here because you have a heat pump installed in our use case here, which is a temperature dependent load. So it is a device that is used for heating, and the colder it is outside, the more electricity it needs to actually heat the building. Then we also provide you with some methods for additional information that you can use to filter time steps. So what you often want to see is you want to look at the data on, I don't know, compare the data of summer and winter months, or compare the data of weekdays to weekends, these sort of things. And what we typically then do is that we just add additional columns to these data frames that allow us to filter better. And for that, you can see an example here. So with these functions, you can just add information. Is it winter? Is it spring, summer? Is it morning or noon? So that is all just calculated from this timestamp here. And then you can just filter on these columns, which makes it easier. So here you then can see, for example, it's very easy to create a printout on the mean energy consumption in summer per 15 minutes, which is then really just one line of code here filtering the data from just using summer months. Then for normalization methods, there are different ways to do so. So if you have a lot of building context data, then you could, for example, also normalize the data by square meters of the building, which gives you a sort of energy intensity value, as it is often called. So how much kilowatt hours per square meter is used. That makes it able for you to compare energy consumption of different buildings quite well. But sometimes you also just, for many machine learning applications, just need other transformations for normalizing the data, like removing the mean, or setting the mean to 0 and scaling it to standard deviation of 1. And that is exactly what you do with this standard scalar here. And then you can see that this is the comparison. So you will just see a shift in the y-axis here from the blue plot to the orange one. But still the patterns itself will be preserved. And of course, you can also use other values. This is just sklearn, an sklearn fit, and you could also use these other normalizers depending on your use case. Then sometimes if you have missing data, you can do interpolations or do some sort of downsamplings, upsampling. So interpolating would be some sort of upsampling, but that of course only works if you want to fill data gaps that are not that big. But if you have like months of missing data, that will not work. But what you can do, as I said, also is like downsampling. That will always work. So just adding, for example, the energy consumption of these 15-minute values to 30 minutes, and then you've got half-hourly measurements. And for that, again, we provide some example here. It's just using the pandas resample method. It's also quite easy. This is an example applied of the different interpolation methods. So you can see here, if these the blue one is the original measurements, and if you would apply a linear interpolation, then it would just linearly interpolate between these values where there are no gaps. And then you have other options like polynomial and spline interpolations. Again, these examples are provided here. Then yes, this also refers to that. And then there is a method that is commonly used to detect outliers. So if you have single erroneous measurements or measurements that are outliers that may screw your machine learning models, it is better to ignore them or to remove them. And what that does is basically, it is a sliding window approach where you set the window size and some parameter that determines how far out of the distribution within this window is the value allowed to be, such that it is not considered an outlier. And yeah, with that, for example, you see an example here where outliers are detected and then removed. And I think that is, are we, yeah, no, three more points on preprocessing. So also quite often you want to estimate the base load, which is basically like the load that is continuously switched on. So if you have some sort of control unit, for example, of the heat pump, this will always remain active and you may want to remove that. For that, we also provide a distribution-based approach that can provide you with this value. And also quite often you may want to see like the small activities and increase these. And for that, you can use some transformation. So for example, just apply the square root or a logarithmic transform to the energy data. And then you will get these sort of small activities way more enhanced. So you can see where on the left here, everything was black and you don't see any small activities. You now see them quite well. Similarly, we provide some options showing you on how you can detect switching activities. I think since we are running a bit out of time, I will not go into detail of that. But yeah, it's basically you can detect if an appliance switches on or switches off. And yes, and then sliding window approaches, as I shortly talked about that, which just means sliding a window over the time series and doing some sort of calculations within these sliding windows. Quite often you also just extract the data from these sliding windows and then use the data from these sliding windows as input to machine learning models so that you increase the size of your data set artificially if you don't have enough smart meter data, for example. So give the algorithm more examples to learn from. Then you can calculate a lot of features from the data and use these as input to your machine learning models. So for example, just calculating the standard deviation, the mean, the median would be statistical features, but these can get arbitrarily complicated. That being said, there are Python packages which do that for you, so you don't need to reinvent the wheel. TS Fresh, for example, is such a package. Again, we provide examples. And we talked about these distributions earlier. So looking at the histograms of the data in the frequency domain, here we provide a method on how you can detect different peaks in these histograms. And what Markus said in the beginning is that these peaks are interesting because if you have resistive loads, which basically have a constant power consumption all the time, then they will show up as peaks in these histograms. So that is an indication maybe for how many appliances you have in this building. And yes, then we provide some methods for Fourier transforms. So shifting the signal of the time series into the frequency domain such that you can see whether what the high and low frequency signals are in this data. And yeah, that was maybe a bit fast towards the end, but yeah, we're running a bit out of time, so I will hand over to Markus for the next one.
Yeah, thank you very much for these preparations, because this brings us to the next sort of section about some concrete applications of the tools we just learned about. And Tobias mentioned non-intrusive load monitoring or load disaggregation, and it's a very big topic. It has been researched for a long time, but the general idea is to sort of figure out what is one individual device up to, what is it doing when you only have the aggregate smart meter data from the whole household. And this can be anything. That could be a toaster or a fridge but maybe most interestingly, it can be like a heat pump or an electric vehicle, which are really the biggest appliances in a household. And like I mentioned, it's a very big topic. It has been like machine learning has been applied to it in like from the simplest to the most complicated transformer model architectures. Everything has been used there. And just to give you an idea and sort of a practical example, what this entails, we sort of built a very simple heuristic detection algorithm and walk you through all the steps in this tutorial. And yeah, what this comes down to for our example is exactly this this curious demand that we saw in this heat map, for example, also in the mean day profile. And what we want to do here is to sort of figure out what device is this, or remove the demand of this device and figure out how much energy does it consume. And because it's a relatively clear pattern, especially in this heat map view, what we basically just do is we apply a threshold. Then we get a better view of like there's high demand or low demand. And then what we make use of is the fact that this device seems to run always at the same time of the day. So this nice pattern that we observe, and we basically look at these plateaus here that we filtered out where the demand is relatively high. We look at when do they actually start, and we see that if we look at the histogram of that, we see they all start sort of in the evening. And now we use this time to sort of say, well, then we only look at those plateaus starting at this time. Then we filter out everything before that. And then we also say that like the device switches on once, switches off, and we only take the first one. And this brings us to this nice extracted pattern of what's going on here in the evening. And then we can just get the power demand of that, or the energy consumption. And so this is an example of having disaggregated the load of this device. And of course, if you're working with unknown data, you wouldn't really know what's going on here. But actually, we do know where this data comes from, and what this actually is an electric water heater. So this makes, in addition to the space heating provided by a heat pump in this case, it creates the domestic hot water used for example, showering. And now that we have disaggregated this, we can actually jump into the next topic and make use of this data to estimate the flexibility that sort of could be provided by an electric water heater, because you can heat up the water basically at any time during the day. And you don't have to do it always at the same time. You don't have to do it exactly when it's needed, but you can just do it whenever the energy is cheap, for example. So that's the idea of figuring out how much flexibility there is in a certain demand or from a certain device. And now using this disaggregated data from the electric water heater, we can, for example, look how much energy does it consume on every day. So this is just summing it up again over the day for the whole time, and we can see already here there's actually some seasonality in the data, but it's not as pronounced anymore as in the whole in the whole data from also the heat pump and all the other appliances. We can also see what is the share of the data from the water heater, from the electric water heater, from the total demand. And then maybe most interestingly, what we sort of come up with here is the comparison of the share of energy consumed in the winter and in the summer. And we can see actually in the summer the share is higher. And this is of course because the heat pump uses a lot less energy in the winter. So there's totally less demand, which means that the water heater has a higher fraction of demand. Because people they shower in summer and winter the same, but they don't space heat their building as much. So this is just, like I mentioned, one very simple overview of what load disaggregation is and what you can do with it. And the field is much, much bigger than that, and there are much more advanced methods than that.
Yes, and then we have actually two more bigger parts. So also anomaly detection is quite a big part. I guess I leave it up to the moderator on how we would want to continue. I mean, we could just walk you through that, but we can also just use the last 15 minutes maybe for questions if there are any, or if there are none, then continue. This is totally up to you. But ultimately, I mean, this is a resource that is provided online that you can also look at by yourself. So in case you have questions, we would also be open to rather answer these. But before I hand back to the moderator, I just want to say where you can actually find this tutorial. So you can find it on the Climate Change AI website. Then if you press here, tutorial, you will find it. You can either just Google the title of this webinar, I think then you will immediately find it. Or if you go here through resources and tutorials, then you will find it somewhere here among these very comprehensive tutorials. So I think here it is exactly on the Climate Change AI website. Okay, so how should we continue? What do you think?
I think we have time. I think we should go for it, the anomaly detection subsection.
Okay, then I will try to do it not as extensive as the previous parts. So what you need to know about anomaly detection is that it's basically ultimately about finding out if there are change points in the data, so where the data really significantly shifts in distribution. And you can either do that, you can do that in two ways. You can either do that as so-called offline change point detection, which is you take the entire data set at once and you look back in time to identify where the change points were. And the second way is to do online change point detection, which is basically continuous observation over time and then identifying the real points in the change points in real time. So really seeing, is it now a change point or not? And that leads to sort of different methods. So for the offline change point detection, the easiest way to do that is basically through a sliding window approach. So you slide a window over and then you see if there is a change in the distribution noticeable. For that, there is a package which is called Ruptures, a Python package with a lot of statistical ways to do that, where you can sort of set different parameters based on your needs. But to provide you an example on what this is able to achieve, this is what is shown. So it really detects quite well. Here is sort of a shift in the distribution where the energy consumption goes down quite significantly, and from then at least changes for a period of time. Also, this is like, the change point detection offline with just a rolling mean, and then finding peaks on the distributions of these means within these sliding windows, basically. And then it identifies these sort of change points. There are also way more complex methods in this domain, which is typically called SAGS, which stands for Symbolic Aggregate Approximation. And that is ultimately a method where you divide data also into different chunks. You normalize the data, and then you chunk it on a horizontal way. So using these gray lines here, for example, as boundaries. And then everything below this gray line, you give it a character saying this is the section A, this in the middle is the section B, and this on top is the section C. And then if you use these different letters as approximation, you will get some sort of words or vocabularies. And in the next step, you can then actually look at the distributions of vocabularies, which gives you an approximation for which words are frequent and which are not. And these frequent words are often called motives, and these non-frequent words that are rather rare are called discords. And this way you can identify typical and atypical patterns. There is also a Python package which does that, which is called SagsPy. Yes, then we provide another example for finding these discords here within our data. And here you can see, for example, that it identified two different sections which rather seem to be non-typical. And with that, I hand over once more for the last part to Markus.
Yeah, so this brings us to the... Yeah,
Markus, I don't mean to cut you off, but I think we have some questions that we could get to if both of you are okay with that.
Yes,
perfect. Yes, like
Yes.
we said, tutorial online, so people can just check out the last part.
Perfect. So The first question that we have is, how can we identify energy savings opportunities using this model?
So, I mean, we showed you a lot of methods on how you can pre-process the data, on what sort of methods you can use for load disaggregation and so on. Identifying energy saving opportunities is a quite big topic in itself, and it depends very much in what way you want to do that and what kind of contextual information you have. So, for example, that is a part that we did not walk through now, but what you can do is you can calculate these sort of energy signatures, which is like energy consumption over outside temperature, and then identify sort of a vector or a curve that is typical for this household. And then you can provide the household, for example, feedback on what would happen if you would reduce your temperature dependence by some sort of value. So move the curve down, and then the gap in between is basically your sort of energy saving potential, meaning you reduce your energy consumption independence of the temperature. So that would, for example, refer to this heat pump optimization. If you optimize your heat pump, you will probably get a pattern which is below this orange curve, and then your potential lies somewhere in between. Of course, again, you would then need to calculate in the next step the actual savings achieved by using the difference at each outside temperature across observations of temperatures for this household. But yeah, it's actually very specific. It's a very complicated topic for which there are different papers out there, but this is just one example.
All right, thanks for that answer. The next question that we have is, can I ask if you have incorporated consumer energy pricing into your work?
So for this tutorial, we have not included any kind of market data, which of course is another big topic in the energy sector. So we really focus on the smart meter data, understanding the smart meter data. But indeed, as we mentioned, additional context information, additional data sources can be very insightful, and especially with the new electricity tariffs, where the customer is exposed to a dynamic electricity price depending on the spot market, for example. This can be really interesting to see the correlations between demand and price and so on. And yeah, why we didn't do this in this tutorial, we of course invite anyone to sort of augment it for themselves, add this data. There's definitely publicly available data for this for Europe and all major markets. So this is indeed another very interesting opportunity.
And maybe what you can also say is, so typically you have sometimes you have different tariffs. So for example, here in Switzerland, you have like a high and a low tariff just by time. So split between two. At night, it has a lower tariff. And then the smart meter uses the so-called OBIS code, which basically you can consider this to be an additional column besides the timestamp, which tells you like information what type of data this is, but it also encodes this information on what kind of tariff is it. So you could actually filter by different tariffs and then see if this household reacts sensitive to the tariff, for example, by switching the loads on or off, depending on if it's in the high or low tariff zone. So typically the smart meter data has like an additional column which encodes that.
Nice, thanks. Can you provide insights on predicting future energy consumption based on previous energy consumption patterns?
Yes, so this is of course the other very big topic in the energy domain of load forecasting, which we have a very brief section in this tutorial, but actually we mostly link to another very great tutorial also from Climate Change AI, which we currently can't seem to share, but it's also linked on the website at the same point that we showed, and this goes in much more detail as it only focuses on load forecasting. But yes, of course, this is a very big topic, and again, all the major machine learning models are applied to that, from regression to transformer models. You find everything in the literature.
Okay, nice, thanks. And yeah, this climate change tutorial should be available on the website, so I do encourage everyone to go check that out. The next question is, how do you see this model being compatible and applicable to the commercial sector?
Sorry, can you repeat that?
How does this model of smart meter data analytics apply to the commercial sector? So I think the question is commercial meters, not residential meters.
So that depends again. So it depends on what the utility company, for example, offers, or if there are ways that other companies get like the allowance of the customer to access the smart electricity meter data through a portal, for example, and then use it for further use. But there are services, for example, which provide insights on energy efficiency. So here at our chair, we collaborate quite a lot with a large utility company in Switzerland, where we have helped exactly to commercialize these models. So to provide feedback to the users on their energy consumption, how high it is in comparison to their neighbors, for example, providing them dashboards of their energy consumption. So yes, there are ways to commercialize that, but again, it depends very much on your specific use case on how you would want to do that. But I think these methods will still be could still be a good starting point for you to develop your own models for your use case.
Yeah, and maybe interpreting the question differently as looking at data from the commercial sector. Of course, you can also apply all the methods we mentioned to any kind of energy data, but even beyond that, to any kind of time series data. And this is also where most of these methods come from. And basically, the way I see the commercial energy sector, it's just what the households do, but even more extreme. So usually it's much bigger loads. They have a much bigger impact on what's going on in the grid. And then also there, it is very useful and insightful to understand what is going on at what time. And questions like flexibility estimations are also very relevant there when a factory starts working or stops working. This is a very big event in the power grid.
Got it. I think we have time for one last very quick question, which is my personal question as well. So thanks to whoever asked this. How to analyze the demand response capability of a household using similar data?
Yes, exactly. So this is again pointing towards the flexibility analysis. So this is what I briefly mentioned after the load disaggregation. So here, if you remember, we had sort of the disaggregated signal from the water boiler extracted from the total demand. And now the idea in a demand response setting would be this boiler doesn't have to run at this specific time. It could as well run a few hours earlier or a few hours later. As long as you have enough hot water in your water boiler, you can use it to take a shower or do the dishes or something. So then we can ask like how much can we shift this and what's the potential even. And for that, for example, one of the interesting plots was how much of the energy of a given day is consumed by the water heater. And this gives you an idea of how much you can shift your demand around. Because of course, if you use your laptop or your PC, you can't necessarily shift that energy around, but the energy of the water boiler you can. And then it's interesting to now see here, what does the water boiler do versus what does all the other demand do?
Yes, and also I think it depends quite a lot on the device that you're actually looking at, because you also have done quite a lot of research on electric vehicle charging, for example, where we investigate exactly how much can we shift the charging to reduce the peak demand of the grid. So typically you plug in, the vehicle is directly charged to 100%, and then it sits idle for quite a while, meaning that you have quite a lot of potential to shift this demand to reduce the peak. And we have developed methods, for example, to predict when will the car be unplugged, such that you know this is your flexibility range for this specific device. And for this water heating, for example, you just want the water heater to run once a day so that you have enough hot water in your boiler. But other than that, you don't care when it's actually running. So that is actually a use case where you have quite a lot of flexibility.
Got it. Well, thanks a lot, Tobias and Marcus, for your time and the presentation and the wonderful tutorial that you presented today. I think we're at time, so we should probably wrap up. I personally love the tutorial even when it first came out, and it's great to have the presenters present it again. And also a huge thanks to the audience for being engaged and attentive. All right, stay tuned for more climate change AI webinars, and I look forward to seeing everyone at some future event.
Thank you.
Bye-bye.
Bye.